Something extraordinary happened after 3I Atlas swung around the Sun. This interstellar visitor, older than our entire solar system, suddenly started behaving in ways that have astronomers scrambling to rewrite their models.
This morning, we have a report that the object got much brighter than expected, and moreover, the color of the object is blue.
The nickel-to-iron ratio in its plume defied every comet we've ever studied. Jets of material erupted at angles that shouldn't exist. And then there's the tricarbon emission, misaligned with everything else, pointing in a direction that makes no physical sense. NASA's most powerful telescopes captured it all. What they found suggests this object isn't just passing through our cosmic neighborhood. It's revealing secrets about star systems that died millions of years before Earth even formed. Let me take you back to November 16, 2025. The Keck II Telescope on Mauna Kea in Hawaii locked onto 3I Atlas, 18 days after it made its closest approach to our Sun. At that moment, the comet was 93 million miles from the Sun and just over 194 million miles from Earth. Now, here's where things get interesting. Before perihelion, before it swung around the Sun, 3I Atlas was already unusual. Its nickel-to-iron ratio was higher than any comet we'd ever observed. Not just a little higher, dramatically higher. This thing was extraordinarily enriched in nickel at distances beyond 155 million miles from the Sun. But after perihelion, something changed. The Keck Cosmic Webb Imager captured spectral data that revealed a strong evolution in that nickel-to-iron ratio. The ratio changed in direct proportion to the comet's distance from the Sun, following a precise mathematical relationship. As 3I Atlas moved away from the Sun, the ratio shifted with a power of 1.15. That's not random. That's a signature. And then there's the water production. Using data from the SOHO spacecraft's SWAN instrument, scientists measured the water output from this interstellar traveler. At its peak after perihelion, 3I Atlas was producing 4 times 10 to the 28th molecules of water per second. To put that in perspective, that's enough water vapor to fill an Olympic swimming pool every few seconds. But here's the kicker. The water production showed a heliocentric asymmetry. What that means is the comet behaved differently on its way toward the Sun versus its way back out. On the inbound journey, water production increased with distance to the power of -5.9. On the outbound journey, it followed a shallower curve, -3.3. The comet was more active going in than coming out, and that tells us something fundamental about what's happening beneath its surface. This wasn't just a comet warming up and cooling down. This was a comet with a distributed source of icy grains, behaving more like the hyperactive comet 103P/Hartley 2 than a typical solar system comet. And remember, 3I Atlas traveled across the galaxy for at least 10 million years without passing another star. Probably much longer. This thing is ancient. Now let's talk about those jets, because this is where 3I Atlas goes from unusual to genuinely bizarre. When scientists subtracted the circularly symmetric glow around the nucleus, they revealed jet and tail features. Multiple emission streams shooting out from the comet's core. Nickel, iron, cyanide, and dicarbon emissions all traced jets emerging at roughly the same angle, aligned with the direction opposite the Sun. That makes sense. Solar radiation pushes material away from the Sun. Basic physics. But tricarbon? Tricarbon decided to do its own thing. The tricarbon emission traced a jet emerging at a completely different angle than every other molecular and atomic species. While nickel, iron, cyanide, and dicarbon were all roughly aligned with the anti-solar direction, tricarbon was misaligned. It pointed somewhere else entirely. This isn't supposed to happen. When a comet heats up, when solar radiation vaporizes its ices, the material should be pushed in predictable directions. The physics is well understood. We've studied dozens of comets. We know how they behave. Except 3I Atlas didn't get the memo. The images from the Keck telescope show excess flux in red and flux deficit in blue. The excess corresponds to emission from jets and tails. The deficit shows up in the anti-tail direction, pointing back toward the Sun. You can see the directions marked clearly, opposite to the comet's motion and opposite to the Sun. Everything lines up except that tricarbon jet. And there's more. The cyanide emission showed a steeper dependence on heliocentric distance than tricarbon and dicarbon molecules. Different molecules were responding to solar heating at different rates, suggesting they were coming from different depths or different compositions within the comet's structure. What we're looking at here is a comet with a complex internal structure. Not a simple dirty snowball. not a uniform chunk of ice and rock. This is an object with layers, with pockets of different materials, with a history written into its very composition. The Rubin Observatory is expected to discover many more interstellar objects in the coming years. When it does, we'll finally have a comparison set. We'll be able to see if 3I Atlas is truly unique, or if this is just what interstellar comets look like. But until then, we're left with this one extraordinary visitor and a growing list of anomalies that don't fit our models. So what does all of this tell us? What's the one killer point we're building toward? 3. I-Atlas is giving us a window into the formation conditions of planetary systems that existed long before our sun ignited. The high carbon dioxide ratio, the unusual nickel enrichment, the complex jet structure. These aren't just curiosities. They're signatures of where and how this comet formed. The carbon dioxide to water ratio is among the highest ever observed in any comet, solar system or otherwise. That suggests 3I Atlas was either exposed to higher levels of radiation than comets from inside our solar system, or it formed in a region of its original planetary disk where carbon dioxide ice naturally freezes out from gas. Both scenarios tell us something profound about the conditions in that ancient star system. The nickel to iron ratio evolution tells us about the comet's composition at different depths. At large distances from the sun, when only the most volatile ices sublimate, we see that extraordinary nickel enrichment. Closer to the sun, as deeper layers are exposed, the ratio shifts towards something more familiar, more like solar system comets such as 9P/Tempel 1. And that misaligned tricarbon jet? That's evidence of internal structure we can't see directly. Different pockets of material, different compositions, different responses to solar heating. This comet is a time capsule, and every measurement we take is like reading another page from a book written millions of years ago in a star system that no longer exists. The Post-Perihelion observations also revealed something remarkable. Stability. No outbursts, no rapid depletion of water production, just steady, predictable behavior driven by solar insolation acting on a stable, active area. For an object that's been wandering the galaxy for millions of years, that's extraordinary. It suggests 3I Atlas has maintained its structural integrity across unimaginable spans of time and distance. This is what makes interstellar objects so valuable. They're not just visitors, they're messengers, carrying information about the diversity of planetary systems across our galaxy. 3I Atlas is now traveling away from the solar system, getting dimmer with each passing day. It's already too faint for amateur telescopes to spot. In March, it will pass relatively close to Jupiter, offering one last chance for deep space observations before it fades into the cosmic background. But the data it left behind will keep scientists busy for years. Every spectrum, every image, every measurement is a piece of a larger puzzle about how planetary systems form, how comets survive in interstellar space, and what the galaxy looked like millions of years ago. The Rubin Observatory will change everything. When it comes online and starts its systematic survey of the sky, we'll discover interstellar objects before they reach perihelion. We'll track them on their way in, watch them swing around the sun, and follow them on their way out. We'll build a catalog of these cosmic wanderers, and with each new discovery, we'll refine our understanding of what's normal and what's extraordinary. If you found this fascinating, hit that subscribe button so you don't miss our next deep dive into the cosmos. Drop a comment below and let me know what part of 3I Atlas intrigues you the most. Is it those misaligned jets, the ancient origins, or something else entirely? And if you know someone who'd love learning about interstellar visitors and the mysteries they bring, share this video with them.